For the next section, I've given you guys a frequency distribution showing the frequencies of squats that people were able to do with 70% of their body weight. So the number of squats are indicated on the x-axis with the frequencies noted on the y-axis. Question 19 is asking us to find the median of the data set shown in the figure. So to do this, we need to use Excel. And I'm going to adjust some of the elements on my screen so that it's a little bit easier to follow along. To find the median, we need to change our frequency distribution into a list of data. So if we go from squat number to squat number, we have 0 occurrences of 11, 1 occurrence of 12, 0 of 13, 1 of 14, 0 of 15, 1 of 16 and 17. 18 shows up twice, 19 shows up twice, 20 shows up twice, 21 shows up twice, 22 3 times, 23 3 times, 24 shows up 5 times, so again, following our frequency distribution here, so that's 1, 2, 3, 4, 5. 25 shows up 6 times, 2, 3, 4, 5, 6. Same thing for 26. Let me scroll down. 27 shows up 4 times. 28 shows up 2 times. Okay, so hopefully it was apparent. I just went through the distribution and then listed each squat or number of squat value, the number of times that was indicated by the frequency column. So now I've got an ordered list of data, and I can easily calculate the median using my median function. And I can see that that value is 24. Okay. What is the mean of the data set shown in the figure? So to find the mean, we can use the average function on our list of data. And let's round that to 2 decimal places. And we get a value of 23.17. The data shown in the graph, we can say, this should be R. The data shown in the graph are positively, negatively skewed, or relatively normal. In this case, because the tail is on the left side, we would say that our data are negatively skewed. Visually, because of what I just said, there is a tail extended to the left of the mean. How do we know based on distribution shape calculations? So the only distribution shape calculations we can run off of these data are skewness and kurtosis. So we'll do our skewness calculations, our kurtosis calculations, and then we can evaluate the z-scores for skewness and kurtosis to see if we have actual skewness. Okay. So sometimes we can see skewness based on shape, but we might not have statistical skewness based on our z-score of skewness. So to find our sample skewness, we use our skew function on our list of data. Standard error is equal to the square root of 6 divided by our sample size. I'm just going to make all of this section 2 decimal places. Z-skew is our sample skewness divided by the standard error. So we can in fact see we've got negative skewness just based on that value because it is less than negative 1.96, which is our cutoff. Now we could see if we have any sample kurtosis. And our standard error is 24 divided by the sample size. Based on this value, we do not have any kurtosis. Okay, so we're negatively skewed. How do we know based on distribution shape calculations? We could say Z-skew, which is negative 2.99, is less than negative 1.96. There is no sample kurtosis because the kurt, which is 1.34, is between negative 1.96 and positive 1.96. Okay. Again, 1.96 represents the criteria of a 95% confidence interval with alphas or regions of rejection both above and below the mean. So as long as our z-score for our skewness and kurtosis are within these two boundaries, that would be considered normal. As soon as we have criteria not met, either having values less than 1.96 or greater than 1.96, that's when we have negative or positive skewness or kurtosis, respectively.